as we go through this, we have the end plates here, or the epiphyseal plates across the ends, and that's where our bone is actually growing. So it grows from the outside, from the ends outward. The center is the first to be developed, and it grows outward. It makes the long bones. Lots of blood vessels, lots of nerves in your bones, so when you break it, they hurt. It hurts a lot to break a bone, and it takes a long time for it to heal in comparison to like a small little paper cut, right? Because it's a very intense little thing and changes. This is what a baby would look like at 12 weeks from conception. Yeah.
What's the first bone to form?
First bone to form. That I'd have to look up. I don't remember that. You got me on that one. Someone will Google it later. Okay. I'm trying to think now. You got me going. Anyway, all the dark red areas, if you see the little hand here, see those little itty bitty, maybe you can't see them from there. You see a little better? You can see these little red areas are the start of their fingers, or the metatarsals, metacarpals, in their hands and their feet. The arm starts to form earlier than the fingers. Remember, from the inside out, we start creating this. Here's the little pelvis, the legs, the feet, hardly even any there at all. And then we have these little plates in the head. See how they look like just pieces of plates? Here's the fontanelle at the top, and when the baby is born, those fontanelles allow the head to become pointed. And that pointing allows the baby to come through the birth canal, kind of like a bullet. It makes this more pointed area. And then after the baby is born, the pressure inside the brain, around the brain, pushes those bones back out, makes this nice little cute little head. Sometimes it's kind of funky looking and for a little while, and then it kind of evens out. And if you leave your baby too long on one side, it may flatten that out. The bones will remodel or not model properly. So that's the way the babies come out. And we'll talk about in AP2 where babies come from. So we have what's called interstitial growth, is growth in the long bones. And appositional growth means thicker. So if you're growing taller, that's appositional. If you're getting fatter, that's oppositional. So interstitial growth is longer, oppositional is wider. Wolff's law, remember this law because there'll be questions on the test on Wolff's law. Wolff's law basically states, to summarize, that the more stress that you put upon a bone, the stronger that bone will be. It has to compensate for the pull of the muscles that you're putting on it. So if your muscles are really big and strong, you have to have super big and strong bones to hold that muscle so it doesn't just snap your bones right off. Right? So the greater the density, the better. So the osteoblasts and the osteoclasts are constantly remodeling your bones to adapt to this stress that you put upon them. So if you're a weightlifter or a bodybuilder, your bones are going to be thicker than if you are very sedentary, somebody working in an office. Right? Wolff's law. Epiphyseal plates. So let's look at epiphyseal plates. We have the long bones, and they have different parts to them. The diaphysis, or the shaft, is the center of the long bone. We have compact bone on the outside of it. Then we have a canal on the inside, the marrow cavity. And then we have some fatty tissue sometimes, fatty marrow inside this also. And then at the end is the epiphysis, and this is the expanded ends. This is where the bones are actually growing. This is spongy bone. Now if we look at the bones that we have, we can see that they are different on the ends than they are at the regular parts. So I'm going to grab, let's grab this one. here's some bones that we're going to pass around. And if you look at these bones, you'll see that this is the diaphysis, the shaft, and this is the end, the epiphysis. And this is, you can see when it goes around, this is like a trabeculae. It's like spongy. If you push on it real hard, it flakes off and breaks. This part's really hard, right? Same way with these. You can see inside the bone is almost like honeycombed. And that's where we have a lot of times the bone marrow and those types of things. Inside here also, if we cut this, this will be hollow for the bone marrow to be in. Pass those around. Anybody know what those bones are? Which bones are they? One is a femur, and one is a fibula. So we'll pass those around. So on the end of the bones, we have an end, and then we have a line behind the end of it, an epiphyseal line, which is a hyaline cartilage line that is constantly growing. And it's a cartilage line that's growing, and at the end of the bone itself, it's very smooth and kind of silky. That's the hyaline cartilage that makes up the joint cartilage. So here is the bone, the long bone. Our epiphysis is this part, the outer part with the epiphyseal plate here. This is the diaphysis, another epiphyseal plate, and the epiphysis here. Same way on this one. Epiphysis is the end of the bone, diaphysis is the shaft. So shaft and diaphysis are the same thing. Questions about that? Those are long bones.
I have a question about why are those bones like, they have like holes like, that looks like stockings, like if you went through stockings, why is it like that?
Holes like a stocking.
Like the neck, the checkerboard pattern.
That's the part of the soft bone, part of the epiphysis, the end of it. It's kind of a trabeculae where it's kind of hollow, honeycombed. Yep. So the epiphyseal plate is where hypertrophy takes place, the growth of the cells, more cells are being laid down, calcification, ossification takes place. The cell is getting, the bones are getting bigger. The more cells, the bigger the cells, the bigger the bones. So someone like Shaq has really long legs. Their epiphyseal plates grow for a really long time and very quickly. Now, sometimes people grow too fast, and that's because of their pituitary giants. They get too much growth hormone, and they keep growing and growing and growing. Sometimes they never stop. Some people, they just grow until they die, and they're like 8 foot tall.
Don't they usually, if they're like super tall, don't they usually die younger? Like once they...
Yep. Some guys like Andre the Giant and some of these, you know, they are very, he was a giant. He actually had a pituitary problem that caused him to be that tall. There's a guy now, he's 8'6" or something like that, and he's still growing very slowly. And he will die. Most of the time their joints falter on them, they get arthritis, they start having problems with walking, and then their heart just gives way because their body is so big the heart can't keep up with the massive amounts.
So it's almost just like a normal-sized person being really...
Normal size heart, just a huge body, trying to push the blood around it. Doesn't work too good. So growth hormone, thyroid hormone, all help make bones bigger and stronger. Growth hormone starts when you hit puberty and you start growing. Up to that point we grow very slowly, have a little bit of growth hormone being produced, but during puberty it goes, you know, sometimes people will grow 6 inches over the summer, right? They just really grow fast. And then other times they don't grow hardly at all. So when you hit puberty and then you get out of puberty, you stop. Adolescence is when you stop growing, and you can't grow again. You'll grow wider, but you're not going to grow taller. Unless you have a problem with the pituitary and it starts producing growth hormone again, that will mess things up a little bit more. Okay, so let's talk about bone growth and repair. Now sometimes people have problems, they are small. Yes, question? Yeah, side of your bottom of your leg. Yep, fibula.
What's the front?
Tibia.
Okay. Sorry, I didn't mean to interrupt.
So some people have problems with growth. Now we have small people or short people, right? The people give them bad names like dwarfs and midgets and all sorts of funny names like this, right? But they're just short people, and there's usually two reasons for them. Two main reasons. One is achondroplasia, right, where they don't produce the proper length of bone, and then you can have pituitary. One that is pituitary. Achondroplasia is a genetic trait. What was that show called? The Big World, Little People, Big World, or something like that. You know what I mean? They had two little people had kids, and what was up with the thing where they had one big kid and one little kid, and then no, three big kids and one little one, right? Is that what it was?
I don't remember, but that's what I was gonna ask.
Yeah. Oh, that's right. Two of them were twins. They were fraternal twins, and then the other kids were normal height. So how does that work? How can have two little people have big people?
Is it just like a recessive?
It's recessive gene. They both had the recessive gene. They were heterozygous for being short. They each got the gene for shortness, but in their genetics they had the gene for tall. So when their babies came out, they got the genes for tall. Now they have a chance. Their kids also have a chance to be small, depending on who they marry. Yes, Guy.
So just like big people, like if you die at a younger age, is that the same thing as little people?
A little bit more. I'm not getting it. I don't understand.
If you're a little person, do you die younger too? Because you're like organs and stuff.
Oh.
Frail?
A lot of times they do die earlier. It could be from respiratory problems or joint problems. They have a lot of joint problems where they have surgeries a lot. Those types of things can affect them a lot. So, and they have to work a lot harder with their heart because they're struggling. They're trying to do more. You have to remember, people like that have to adapt to our world. So even getting something off the top shelf, they have to crawl a ladder instead of just raising their arm up and picking it out. So they're working a lot harder all day long, every day, to do daily tasks that we would. So yeah, it's harder on their heart and harder on their joints to be little people. You know, and then, of course, then they get picked on too. So, mini-me, you know, and some of these people, that's just what they are. They're just have had a genetic situation. Now, pituitary dwarf is, they have less hormones being produced by their pituitary, which is right behind, it sits in the sella turcica. What bone's the sella turcica on? Sphenoid. Very good. Thanks, Jenny. So let's see here. Whoops. I got to show you this video. One of my favorite videos. Yay! So, were those little people or were those kids? They were both. They were both. Some of the little people were kids, but a lot of them were little people, actual little people in the Wizard of Oz. I think the last one died a couple years ago. It hasn't been. When did the Wizard of Oz come out? Anybody have any idea?
It was like 45.
Yeah, very close. I think it was like 45, 46, somewhere in there. 1945. That's a long time ago, right? So bone remodeling. Our bones are constantly changing. We're tearing them apart, putting them back together, making them stronger, making them taller, wider, thicker, to accommodate the pressure that we're putting on our bodies, or just because of the hormones that we're doing. So we're constantly changing them. You'll get a new body about every 12 years.
You
Some
born
of-
every 12 years?
Yep, some remodel very quickly, others take a long time. Your wrist bones take longer than, say, your femur does to lay down new bones. Yes?
So every 12 years in your body changes, or therefore your bones get stronger or weaker?
Depends. Just depends on what you're doing. If you're not eating properly, you're trashing out and drinking a lot of pop and things, you could have and it's not like you wake up one day and say, boom, I got new bones, right? It's a gradual 12-year process. It's not quick. So what you do now is going to dictate how your bones are in the future. See? Leo, question?
Nothing. I just got too philosophical for a second. It made me like, am I the same person I was 12 years ago then? Or do I just like, did my memories just like replicate? And then, okay, stop. I don't want to do this.
Too much existentialism here, guy. Come on. You're the same person, Leo. It's okay. So the osteoclasts break things down. The osteoblasts build them up. Okay, that's the main thing to remember about this stuff, right? We use acids, we use lysosomes to do this, to accomplish this, to break these matrix down. But that's what we're doing. We're constantly remodeling, continually remodeling against gravitational forces, mechanics that we're doing, the diet that we do, all affect this, right? So if I take you up into space, what is that going to do to this remodeling process? Will it affect it? How? Yeah, you actually lose a lot of different things. You become taller though, because you're taking away the compressive forces in your little intervertebral discs. You actually come out taller than you went in to space. But you don't have as much stress upon the body, so now instead of Wolff's Law, it's kind of a negative Wolff's Law. You're not putting stress on the body, you're just floating around. I'm not walking, I'm not running, That's why a lot of them have like a treadmill up there, or they have weights that they do while they're in space, just to increase that resistance to keep their bones strong. Because if you're up there for a year, you lose a lot of mass on your bones.
So, like, if you went up into space and then you came back down, would you be taller?
Mm-hmm.
Would you eventually shrink back down?
Yes, very quickly. Probably within a week. All it does is those little vertebral discs fill up with a little bit more water, and when you put pressure on them, it squishes the water back out. Yes?
How do astronauts lift weights in space?
It's just lighter. They'd be able to lift more.
They have a resistance, so like if they'll hook it to the side of the ship, and then they'll pull on it like a rubber band or something, instead of lifting weights, because you're right, the weight would just float, right? So they have a resistance bands and stuff like that they use. Yeah. Good question, though. It's a good thought. So calcium is necessary for a lot of different things, and these are some of the things that we use calcium in the body, and we get calcium from milk, and we get it from green vegetables. There's not much probably as in comparison to from kale to iceberg lettuce, but we still get some in like broccoli and some of these different really green deep ones. So nerve impulses, muscle contractions, blood coagulation, some secretion in the nerve cells need calcium, and cell division has to have calcium. So if you're not eating calcium, if you're not getting it in your diet, your body will take it from your bones to make sure that this stuff is being done. Right? These are important things. If you're using calcium for your brain to work, to function, it's going to take the calcium out of your bones and put it in your bloodstream to take it up to your brain so that your brain functions properly. Your body doesn't care about your big toe. Who cares? Let it fall off. But we want to think about your brain, right? We want to make sure your brain is quick and sharp, because, look at, prehistoric man. If his brain wasn't sharp, he's going to get eaten by the saber-tooth anyway, whether his big toe is there or not. Right? So we have to make sure that we have that in place. Same with coagulation. It doesn't do any good to bleed to death if you have strong bones. So we're going to take it out, right? Yes?
I was wondering why hands broke so easily. Because,
Hands break so easy?
I mean, it's like if you punch someone in the head,
it's gonna hurt you a lot.
Yeah.
Like,
Yeah.
It won't just be simple, but like considering circumstances and like how people were like territorial throughout history and stuff, and kind of like had to fight in the wild. Why would like our hands be so fragile? Is that
Well, if you were a caveman, your hands wouldn't be quite so fragile, for one thing. You have really thick, according to Wolff's Law, the more pressure you put upon them, the bigger your fingers get. If you ever look at a farmer's hands or an Amish person's hands, their hands are like as big around as your wrist. Their fingers are huge. You know, they're just big because they use them every day, milking cows, pushing a plow, whatever they do. It makes a lot of stress on those fingers, and they get bigger and thicker. I have very small little fingers compared to some people have huge. You know, some guys have size 12 rings or 14 size rings. You know, and I got like a 10, maybe a 9. So yes, Bailey.
Well, if someone like walks every day, then why do toes work so easily? Because aren't you putting stress on your toes for walking? Or like balancing?
Well, it would if we didn't walk with shoes on. Remember, we're kind of protecting our toes and our feet. You know, if we were walking every day on rocks and things, our toes would be stronger also. But yep, and they're smaller. They're gonna, if you get stepped on by a horse, you know, it's just a question of mass over mass. You know, that little toe is not as strong as that horse's foot, and something's got to give.
So is that kind of like, not necessarily that, but like basketball players are more likely to be tall because of like they're constantly jumping and stuff like that, you know?
No, not taller that way, but stronger bones maybe. You know, that's gonna make their oppositional growth better, not their length different. That's more genetic or hormonal for that. So calcium deposits, we can have different deposits in different places, in your arteries, in your joints. Arthritis is a deposition of calcium in the joints that makes you so you can't move very well. Just like in your house, if you have an old house, sometimes the pipes have to be replaced because there's so much calcium inside the pipes that the water doesn't flow through them. That's what happens to our bodies too. So we need calcium for our lungs. We need them for our brain, eyes, muscles, tendons, all these different places, and we can have calcium deposits in any of those places. It can cause problems. Now, what creates this, or what makes our calcium levels the way they are? It's basically hormonal. 2 hormones basically provide us with the amount of calcium in our system that we need. We have parathyroid hormone and calcitonin. Those 2 hormones are specifically designed to make sure that we have enough calcium in our bloodstream or in our bones at any one time. If we don't have enough calcium in our digestive system in our bloodstream, our body will send in calcitonin, and it will take if we have too little calcium in our bloodstream, it sends in parathyroid hormone and takes the calcium out of the bones and puts it in the bloodstream. If we have lots of calcium in our bloodstream, it will take the calcium out of our bloodstream and put it into our bones by calcitonin. So those 2 hormones are the ones that affect the osteoblasts and the osteoclasts. They stimulate the tearing down of the bones with the PTH, or the calcitonin increases the mass of the bones by putting calcium from our bloodstream into the bones. Okay? So we need to do this. Also, there's another chemical called leptin. This helps to inhibit the osteoblasts. And leptin, if we inhibit the osteoblasts, what would that do to the bones? Osteoblasts.
Make them expand.
What's that?
Make them expand.
Make them get bigger? We're inhibiting the osteoblasts now. The blasts are the ones that build them up.
Inhibiting them?
Yep, we're inhibiting the osteoblasts. Make them smaller, right? You're going to have weaker bones by doing that. So Leptin acts reduces the cancellous bone, and it inversely increases the cortical bone. So, okay, we're getting close to the end here.